Okay, this form of modulation uses a polar non-return to zero digital signal, which so now we have logical ones take a value of 1 volt, logical zeros take a value of -1 volt, so it's still 1 0 1 0 0 0 0. This is still a random string of ones and zeros. Logical ones are 1 volt, logical zeros are -1 volt. We take this signal into a mixer as before and mix it with a carrier signal, amplitude AC, carrier frequency F sub C, and this will give us a phase shift keyed signal, and we'll see that when we look at the pictures. But it still is we're still multiplying m of t times AC cosine 2 pi fct. This gives us a modulated signal, which is exactly the same form as the amplitude modulated signal, but it's different in this case because the message signal is either a +1 or a -1, and that's multiplying our carrier signal. When we multiply the two together, we get this phase shift keyed signal, PSK. This is phi PSK, which is equal to the message signal of T times AC cosine 2 pi FCT. So when the message signal is a 1, we get the carrier signal straight up. And when the message signal is a 0, the message signal is -1. This is for a logical 0. We get -1 times the carrier. That gives an inversion to the carrier signal. So there's a phase shift from a phase of 0 degrees to a phase of 180 degrees. And then when it multiplies by a +1, we get another phase shift of 0 degrees. So the phase is changing, phase of 0, 180, 0, 180, 0. Information from the binary signal is found in the timing of these 180 degree phase shifts. And you can see in the diagram, you can see where these phase shifts occur. It's kind of subtle, but it is clearly you can see this in the signal. Now the spectrum, if we have the spectrum of the carrier signal, is a pair of delta functions, as always. The spectrum of the polar non-return to zero signal, so we work that out mathematically. Polar non-return to zero is this sine squared shape that there are no delta functions. It's simply the sine squared shape that has a zero, a null at the bit rate, and then again at twice the bit rate. I used MATLAB to simulate the Fourier transform of this binary signal, and this is the result I got, and exactly what we would expect. This is the envelope of this would be the sinc squared shape. Again, it's got this randomness because I took a Fourier transform of a single sample, and that accounts for the randomness in the spectrum. But the envelope of this clearly has that sinc squared shape. The bandwidth to the first null is equal to the bit rate, and as always, when we're taking a message signal and multiplying by a carrier, we're going to take the spectrum of the message signal, and that will be convolved with the spectrum of the carrier, so we will get this shape shifted and replicated at the carrier frequency. So I had MATLAB take the Fourier transform of this phase shift keyed signal, and sure enough, this is the result. This message signal shape is shifted and replicated at plus and minus the carrier frequency, and the overall bandwidth is twice the bit rate. I want to introduce another way of looking at these phase shift keyed signals. And it's called the constellation diagram. So if we look at a sinusoid in general, cosine 2 pi fct minus phi degrees, so we have an amplitude of 1 just for convenience sake, a frequency fc, and a phase angle shift of phi. We can express this as the real part of e to the power of j times 2 pi fct minus phi. Multiply through the j, so we have e to the j 2 pi fct minus j phi. Break this exponential into two terms, and we could write this as the real part of e to the j 2 pi fct times e to the minus j phi. Back in circuits class, you learned to express this cosine as a phasor. So you would draw a phasor diagram, and if you were to draw a phasor diagram of this complex of this phasor, we would draw the real axis and the imaginary axis like this. Then we would express this cosine as a phasor. It has an amplitude of 1. It has an angle of minus phi degrees. So you would draw the phasor like this. It has an amplitude of 1. It has an angle, this angle is minus phi degrees. And this phasor, this would be 1 times e to the minus j phi. That's the phasor representation for this cosine. Now we can, I want to do the same thing, except instead of drawing an arrow, we'll draw again the imaginary and the real axis. Then instead of drawing an arrow, let me just draw this as a single point on the complex plane. This is still 1 e to the minus j phi. Phi is this, minus phi is this angle again. And instead of drawing the arrow phasor, just draw the dot at the tip of the arrow. And now we've drawn a constellation diagram for this signal. Now it's not a very interesting constellation because it's only got one star in the constellation. But we'll find with these phase shift modulated signals that the constellation diagrams are a little bit more interesting. So we have the polar non-return to zero signal, that logical 1s are +1, logical 0s are -1, and that's taken into a mixer with a carrier signal of constant frequency and constant amplitude. The signal that comes out is simply the two multiplied together, m of t times, in this case, I made the carrier amplitude 1 for simplicity's sake. So we've got two possibilities. For a logical 1, the message signal has a value of +1, and then the phase shift keyed signal is going to be cosine 2 pi fct. And for a logical 0, the message signal has a value of -1, and the phase shift keyed signal is minus cosine 2 pi fct, but I'll incorporate the minus sign into a phase angle shift, so it's cosine 2 pi fct minus 180. Now we can draw phasor diagram for both of these signals. I'll draw them together here on the same complex plane. This is the real axis. This is the imaginary axis. For cosine 2 pi fct, this is a phasor with an amplitude of 1. So for a logical 1, the phase shift keyed signal is cosine 2 pi fct with a phase angle of 0. So the phasor representation is 1 times e to the j 0. Well, we can show that. We would normally show that as an arrow along the real axis, but now let me just put a dot at the tip of the arrow. So this is 1 unit from the origin to the dot, And this is for a, that's the point in the constellation for a logical 1. If the signal is logical 0 and the message signal is -1, the phase shift keyed signal cosine 2 pi FCT minus 180 degrees. Phasor representation is 1 at an angle of minus 180 degrees. So this is minus 180 degrees. So the dot will be, let me see, 1, 2, 3, 4, 5. 1, 2, 3, 4 be right there about. And that's the second point in our constellation. This is for a logical 0. Okay, so we can describe this phase shift keyed signal in terms of its constellation diagram. Logical, the point for logical 1 is along the real axis. This is a unit 1, a value of 1 from the origin, and for logical 0, it's this point at -1 along the real axis. Now let's consider demodulation of this phase shift keyed signal. We take the phase shift keyed signal, which, to remind you, we take the phase shift keyed signal, which is either has a phase angle of 0 or a phase angle of 180 degrees, into a mixer with a replica of the carrier signal, and then through a low-pass filter, and then through a comparator. This is just like when we did amplitude modulation. This is synchronous demodulation. And we have two possibilities for the phase shift keyed signal. If the message signal is a logical 1, the phase shift keyed signal is cosine 2 pi FCT with a phase angle of 0. And if it's a logical 0, the modulated signal is cosine 2 pi FCT minus 180 degrees. We've let the amplitudes equal to 1 just for simplicity's sake. Now, the signal that comes out of this comparator, we've got M of t. See, we're going to have a comparator operating on the output of a low-pass filter, which operates on the output of this mixer, which is going to be the phase shift keyed signal. So let's start for a logical 1. We have the phase shift keyed signal cosine 2 pi FCT times the replica of the carrier cosine 2 pi FCT. So we've got the comparator operating on the low-pass filtered version of this signal with cosine times a cosine. If we apply the trig identity, we get a 1/2 cosine of the difference of the angles. So that's going to be 1/2 cosine of 0. Cosine of 0 is 1, so that's simply 1/2 plus 1/2 the cosine of the sum of the angles, which is going to be 2 pi times 2 FCT. Then the low-pass filter has a bandwidth that will eliminate this high-frequency component. So we have the comparator operating on 1/2. And let's say the comparator makes this value go to a 1. So we've now recovered the logical 1. We've recovered the message signal for the logical 1. If, on the other hand, the input is a logical 0, then M of t is going to be equal to the comparator operating on the low-pass filtered version of, for logical 0, we use cosine 2 pi FCT minus 180. Cosine 2 pi FCT minus 180 degrees times times the replica of the cosine, or the carrier, cosine 2 pi FCT. So this will be the comparator operating upon the low-pass filter version. And now, when we apply the trig identity, we've got the cosine times a cosine gives us 1/2 cosine of the difference of the angles. And when we take the difference of the angles, we get 2 pi FCT minus 180 minus 2 pi FCT. That just gives us cosine of minus 180 plus 1/2 the cosine of the sum of the angles, which is going to be 2 pi FCT, 2 FCT minus 180 degrees. Cosine of minus 180 is minus 1, and the low-pass filter eliminates this high-frequency term. See, this is at twice the carrier frequency. Phase shift doesn't matter to us here. So this second term is eliminated, and we get the comparator operating upon minus 1 times 1/2, and we can map that to a -1, and we have now recovered the message signal for a logical 0. So then with decoding, the string of the binary string of 1s and 0s can be reconstructed.